Okay, the next two are a little trickier, but are dealing with a similar situation, but we have to drop a little vocab before we get into them. The first thing we need to talk about is the arithmetic mean. So this is the mean that you've been dealing with since probably elementary school, where you add all them up and you divide by how many there are. So I might get like the arithmetic mean of our last test score where we add them all up and we see what basically it's just the average. That's not what we're doing today. Today we are dealing with another kind of mean. We are dealing with the geometric mean. So if we're finding the geometric mean of two numbers, so if I ask you to find the geometric mean of 9 and 10, for example. If I was doing the arithmetic mean, I would add them together and divide by 2, and I'd get like, what, 9.5? Well, of course, because that's the average of 9 and 10. But with the geometric mean, you're going to set up a proportion. So if I'm finding the geometric mean of 9 and 10, all you do is you have to take 9 and you have to put it in two different spots of the proportion. So I could put it here and here, or I could put it here and here. Doesn't matter. So I could just go 9 and 9, and then the parts that occupy the other two positions are 10 and x. So another way to set this up could have been, okay, I'm finding the geometric mean of 9 and 10. I just need to mention 9 twice in a way that they occupy two different positions. So I could have gone 9 and 9 here, and then as long as 10 and x fill up the other two, I'm all good. So I could have gone like x and 10. And either way, when I simplify, I get 9 times 9, which is 81, is equal to 10x. And then I divide both sides by 10, and I get 8.1. And that tells me that the geometric mean of 9 and 10 is 8.1. Now, at this point, I'm not going to say exactly why we do the geometric mean, except that it's used within our theorems today quite a bit. So, draw the exact same picture for this theorem that we had for the last one. So we draw a right triangle, and then we draw an altitude from the right angle to the hypotenuse, where it makes a 90. And this forms our three triangles again. And from the last theorem, we learned that all three of these triangles are similar to one another. So with this one, I'm going to go ahead and name it let's see here, how do I want to do this one? I'm going to name it A, B, C, and D. And this one says, so this theorem, so this one has been proved. This is a theorem that says the length of the altitude is the geometric mean, which we just learned and we're going to get into here in a minute, looks like I'm writing off the page a little bit there, so I'll go under here, is the geometric mean, make sure everything's on there, is the geometric mean of the lengths of the, let's say, of the two lengths of the hypotenuse. Okay, this sounds a lot more complicated than it actually is. So the words geometric mean pop up right here. So whenever you see geometric mean, you know you're going to have to set up that proportion that we were talking about earlier. So in this case, the length of the altitude is the geometric mean. So that's like your first number. So whatever appears before the words geometric mean is what gets mentioned twice in different occupying spots of your proportion. So if it says the length of the altitude is the geometric mean, that means that the altitude is mentioned twice in your proportion. So you would put it here and here, or here and here. So in this case, the length of the altitude is AD, and it's the geometric mean of the two parts of the hypotenuse. The two parts of the hypotenuse are BD and DC. So let's illustrate this one with numbers. So let's go ahead and let's see what would be a good one. So let's say this was X, and we knew that this was 6 and that this was 3. Okay, so when you first start doing any right triangle problem, the first strategy that I use is the Pythagorean theorem. We can't use it here for obvious reasons. Then I usually try trigonometry, and if I can't, you might be able to get this problem with trigonometry eventually. But after that, they're probably wanting to use one of these other right triangle theorems, like the ones that we're learning today. And it might be, oh, well, maybe I could use the fact that all these triangles are similar to one another. But whenever I see that the altitude is mentioned, or the altitude is what I'm solving for, I know that they're probably steering me towards this theorem here. So I know that I need to set up a proportion where the altitude is mentioned twice. Since the altitude is the geometric mean, it is mentioned here and here. Also could have been here and here. So it's the geometric mean of the two parts of the hypotenuse. And I cross multiply and I get x squared is 18. And then I get x is the square root of 18. And then the most professional way to write my answer, of course, is as a simplified radical. And what are two things that multiply together to get 18, where one is a perfect square? X would equal 9 times 2, and the square root of 9 is 3. And the answer, the best answer that you could have for this one is 3 times the square root of 2. So today when you're doing your problems, if you notice that the problem, you're going to have this situation over and over again, the whole thing with the right triangle and the altitude going to the hypotenuse. If the altitude is mentioned, they're probably steering you towards this theorem.